tayo sa special purpose subsystems. Una is yung packaging and cooling. The chip package provides mechanical and electrical connection between the chip and the circuit board. It is no longer possible to separate the design of a high-performance IC from the design of the chip package. Next one is the properties of an ideal package. So, una is connect signal and power between the chip and board with little delay or distortion. Next one, removes heat produced by the chip. Third one is the protects the chip from mechanical damage and thermal expansion stress. The last one is inexpensive to manufacture and test. So provide good signal and power connections. The package must offer short wires ito yung mga package sampling dual inline package or DIP. Input and output niya is 840, 1620, 2840, 64. Description, 2 rows of through holes, pins on 100 mil centers, low cost, long wires between chip and corner pins. Next. Chip to package connections. Conventionally, chips have been connected to their packages through thin 25 micrometers gold wires bonded to metal pads. The pads are organized into a ring around the periphery of the chip called the pad ring. The minimum pitch of the pad is limited by the bonding sheet of approximately 100 to 200 micrometers. Thus, 1 square centimeter chip is limited to several hundred input outputs. Chips with a large number of input-output subsets are pad limited, meaning that the chip size is determined by the pad frame rather than by the logic within the chip. The next is the pad wire connect to a metal LED frame to the package. This LED frame distributes the input output to the periphery of the package and is meant to form the pins of the package. Many packages also include a heat spreader to help distribute the heat from the die across the package and ultimately out to the heat sink. As you can see in the figure 13.2, cutaway of a dual inline package showing a corner of the chip with band wires connected to the LED frame. Next one is the package parasitics. The figures show a model of an integrated circuit package. The band wires and LED frame also with parasitic inductance in the signal traces. They also have some mutual inductive and capacitive coupling to nearby signal traces, potentially causing crosstalk when multiple signal switch. The ground wires also have inductance from both band wires and the LED frame. Moreover, they have non-zero resistance, which becomes important for chips drawing large supply current. High performance packages often include bypass capacitor between and the ground. As we will see in this section, the bypass capacitor have their own parasitic resistance and inductance that limits their effectiveness. Next one is the temperature sensors. If a cooling fan motor fails or air intake vent become clogged, a chip may rapidly overheat to the point of self-destruction. Moreover, chips are normally designed to function correctly in the worst case environment. Example is the 70 degrees Celsius inside the system box, so they could operate at higher power and performance level at temperature. Most high-performance microprocessor now includes one or more temperature sensor placed at spot on the die for adaptive control. The most common method of sensing temperature in chips is based on the relationship between absolute temperature, collector current, and the base emitter voltage. for a bipolar transistor. Ito yung formula niya. Tapos, next one. This equation, Q is the charge on an electron and K is the Boltzmann constant. I is a function of transistor geometry and processing, and is also highly sensitive to temperature. Next one is power distribution. An ideal power distribution network has the following properties. First one, maintains a stable voltage with little noise, provides average and peak power demands, provides current to serve as for signal, avoid wear out from electromigration and self-heating, consumes little chip area and wiring. Last one is easy to lay out. On-chip power distribution network. Here, the on-chip power distribution network consists of power and ground wires within the cell and more wires connecting to the cell together. All cells contain internal power and ground buses routed on metal 1 or metal 2. These wires are typically wider than minimum to provide lower resistance and better electromigration immunity. Next one is the IR block. The resistance of the power supply network includes the resistance of the on-chip wire and bias. The resistance of the wires are soldered bound to the package. The resistance of the package or traces, and the resistance of the printed circuit board is because the package and printed circuit board typically use copper that is much thicker and wider than on-chip wires. IR drop arise from both average and instantaneous current requirements. The instantaneous current may be much larger than the average drop because current drop tend to locally spike near the clock edge when many resistor and gauge pitch simultaneously. Next one is the substrate noise. The body terminal of back CMOS transistor is connected to the substrate or well. The P-type substrate for an NMOS transistor is normally connected to the ground, and the N-well for the PMOS or a PMOS transistor normally connected to the VGT. The connection is made through a relatively high resistance substrate or well contact. Substrate noise is also a problem for mixed signal design where separate power supplies are used for noisy digital circuit and quiet analog circuit. The substrate and well should use plenty of contacts guarantee a low resistance path to the power network. Modeling and analyzing substrate noise is beyond the scope of this course. Energy scavenging. Energy sources are the chronic challenge for portable systems. Most systems use batteries which eventually require replacement. This ranges from annoying to downright difficult, changing the battery in the implanted pacemaker. Energy scavenging is an emerging field with tremendous promise for ultra-low power systems. The idea is to extract enough energy from the environment to operate the device. That's it.
So, yung report na to is supposedly kay Shan, pero dahil she's sick, nga, i-report ko yung report niya. So, the topic is all about clocks. Logical clocks are idealized signals with no skew used by the logic designer when describing the systems with a hardware description language. Yung clock skew, the arrival time differs somewhat from one point to another. So, yung difference na yun is yung tinatawag natin clock skew. Yung clock na to is ideally dapat no skew, walang difference. So, a system using two-phase transparent latches requires two logical clocks. Unfortunately, mismatched clock network paths and processing and environmental variations make it impossible for all clocks to arrive at their ideal times. So, the designer must settle for actually a multitude of skewed physical clocks. Therefore, most systems distribute a single global clock. The term clock skew has been used informally in many ways. We define skew as the difference between the nominal and actual arrival time of a pair of physical clocks. But we refer to call intentional delay, so delay, and reserve the term clock skew to account for unintentional differences in clock arrival times. So, kaya ang ginagamit natin ngayon is delay, hindi skew. So, the actual clock skew between two clock elements varies with time and is different from one chip to another. Moreover, it is unknowable at design time. From the engineering perspective, so sa atin, a more useful parameter is the clock skew budget. So, yung clock skew budget should be larger than the actual skew encountered on any long or short path on the working chip, yet no larger than necessary lest the chip be over-designed. So, ito yung isang waveform ng skewed clock. Yan. Clock skew sources can be classified as, so, meron siyang systematic, random, drift, at saka jitter. So, ito, simple clock lang siya na with distribution network. So, simulan natin sa systematic clock skew. Yung systematic clock skew, it is the portion that exists even under nominal conditions. This component can be predicted by the simulation. So, yung systematic clock skew, nakukuha siya gamit yung kahit anong simulations. Another is yung random. Random component of skew is caused by manufacturing variations that could affect the wire width, thickness, or spacing. So, yung random na yun, depende na yun sa design natin, kaya nagkakaroon ng delay. Another is drift. Drift is caused by time-dependent environmental variations that occur relatively slowly. And last one is yung jitter. Jitter is caused by high-frequency environmental variation, particularly power supply noise. This noise leads to delay variation in the clock buffers and gaiters in both time and space. Jitter is particularly insidious because it occurs too rapidly for compensation circuits to be able to counter it. So, ito yung isang clock system ng architecture, isang design. Meron siyang external clock, clock generation, and clock distribution hanggang sa tsaka yung mga clock elements. The chip So, next topic is the global clock generation. The global clock generation receives an external clock signal and produces the global clock that will be distributed across the die. So, in simplest case, the clock generator is simply a chain of buffers to drive the large capacitance load on the clock distribution network. Clock generators are either phase lock loops or yung PLL and delay lock loops and yung DLL to regulate the delay to a constant value in the presence of variation and noise. Ito yung diagram ng zero delay buffers using PLL, at saka yung DLL. So, PLL versus DLL. So, ano nga ba yung pinagkaiba ng dalawang? So, the main difference between a PLL and a DLL is that yung PLL, gumagamit siya ng oscillator that creates a new clock, whereas the DLL naman, gumagamit naman siya ng variable delay line that simply delays the input clock. So, yun nga, yung PLL, oscillator ang ginagamit niya, while yung DLL, gumagamit siya ng variable delay line. Bandwidth and stability. So, if the disturbance is the input clock jitter, we may want the loop to respond slowly so that the output clock will track the average position of the input clock and thus have lower jitter. And another critical metric is the stability. Hindi lang yung bandwidth. So, stability describes how reliably the feedback loop converges to the condition. Generally, so yung PLL require more attention than DLL in order to achieve a good stability. So, yung frequency multiplication naman sa global clock, it can be easily achieved with the PLLs by inserting a frequency divider in the feedback path. So, after nung isa is distribution naman ngayon. After ng generation, distribution. Paano nagkakaroon ng nadidistribute yung global clock? So, the global clock must be distributed across the chip in a way that reaches all the clock elements at nearly the same time. Yung global clock, kailangan niyang marating yung mga elements na kailangan may delay or naka-time at nang sabay-sabay. So, the clock distribution system must be carefully designed to equalize the flight time between the clock generator and the clock receivers. Global clock distribution networks can be classified as grids, H3s, spines, ad hoc, or hybrid. So, first yung grid. A clock grid is a mesh of horizontal and vertical wires driven from middle or edges. Ito yung another is yung H3s. Kung makikita nyo, pa-letter H siya, kaya tinawag siyang H3, is a fractal structure built by drawing an H shape, then recursively drawing H shapes on each of the vertices. And with enough recursions, the H3 can distribute a clock from the center to within an arbitrarily short distance of every point on the chip while maintaining exactly equal wire lengths. So, equal yung mga lengths ng wire na ginamit dyan. Sa spine naman, as with the grid, the clock buffers are located in a few rows across the chip. Pero, instead of driving a single clock grid across the entire die, yung spine naman is the spines drive length-matched serpentine wires to each small group of clock elements. So, if the loads are in uniform, the spine avoids the systematic skew of the grid by matching the length of the clock wires. So, minamatch niya yung haba ng isang wire. Local clock gators. Ano naman yung mga gators na to receive the global clock and produce the physical clocks required by the clock elements. So, kung magdidistribute ka ng mga global clocks na yon, ang unang tatanggap sa kanila yung local clock gators. So, yung, as the name itself, gates, para bago sila mapunta dun sa mga elements na kailangan i-time. So, the output of the gators typically run a short distance to the clock elements. Siyempre, mabilis lang yung switching, kaya kailangan short distance lang siya. So, clock gators are often used to stop or gate the clock to unused blocks of logic to save power. Then, adaptive is the skewing. So, adjustable delay buffers can compensate for mismatches in clock distribution delay along various paths. So, ito yung example ng isang digitally adjustable delay line. The loop bandwidth is low enough to ignore the jitter, but high enough to compensate for temperature drift. So, this technique is sometimes called adaptive de-skewing. So, ito yung example na to is, in the Pentium 4, the delay line is adjusted using a scan chain through the boundary scan test access port. So, 46 phase comparators yung ginamit dito, measures the phase of clock gators.
So, good evening, classmates. My report is all about PLS and DLS. So, this will be the continuation of the report of Sean. So, PLS, or phase lock loop, is a feedback system that generates a signal that has a fixed relation to the phase of an incoming reference signal. So, this is the phase difference. Notice that magkaiba yung frequency nila, but still, the phase difference remains constant. Basic PLL consists of the three basic elements: the reference signal, which is the input, the phase detector, the VCO, the voltage controlled oscillator and the loop filter. Now this the phase detector has two inputs, which is the reference signal and the output of the VCO. Then it will go to the loop filter, then to the VCO again, and then a signal will be may lalabas na signal na. So, phase comparator detector, based dun sa meaning niya, comparator, it just compares the phase of the two signals. The loop filter, basically a low band pass filter. It filters the output from the phase of the comparator based on the block diagram kanina. So this is the reference, this is the phase detector, and the proportional phase difference. So, the voltage-controlled oscillator, ito yung final stage of the basic PLL circuit. It generates the output radio frequency signal. So, yung graph ng frequency versus the voltage versus the frequency is dapat linear. So, or pa-curve, basta as the frequency increases, the voltage increases. Kapag ganito, na nagkaroon ng downside, the circuit will not work well. So, this was explained a while ago. So, the principles of PLL, ginagawa lang niyang in phase yung dalawang signal through differentiating the phases of the signal. So, this is the frequency versus the voltage. So, kapag nag-straight na siya or wala nang phase difference, meaning lock na yung or okay na yun. So, these are the PLL applications. Di natin alam, pero yun yung mga nakalagay sa cellphones natin, satellites, radars, and other communication systems. So, another is the DLL or the delay lock loops. This was also discussed a while ago sa report ni Sean. So, the difference between a PLL and DLL is that PLL uses VCO while this uses VCL. This is, VDL pa, which is the delay line. So, same functions lang ng phase detector sa filter or nagkaiba lang is delay line. So, PLL and DLL are used in integrated circuits in technologies nowadays, normally in computers and communication systems. So, difference is that PLL uses VCO while DLL uses delay line, and DLL is much better than PLL because mas konti na yung errors kay DLL.
My report is about input and output subsystems. Input and output subsystem is responsible for communicating data between the chip and the external world. This has the properties, drives large capacitances, typical of off-chip signals, operates at voltages levels compatible with other chips, provides adequate bandwidth, limits slew rates to control high-frequency noise, protects chip against damage from electrostatic discharge or the ESD, protect against over voltage damage, and has a small number of pins. Therefore, it has a low cost. So first, we start with the input and output pad design. This pad consists of a square of top-level metal of approximately 100 Rm on a side. The term pad sometimes refers to just the metal square and the other times to the complete cell containing the metal of the electrostatic discharge protection circuitry and the input and output transistors. So first, the circuits. There is a VDD and the ground pads. These VDD and the ground pads are simply squares of metal connected to the package and on the chip power grid. Most high-performance chips devote about half of their pins to power and ground. So, this large number of pins is required to carry the high current and to provide low supply inductance. Next is the output pads. Output pads generally contain additional buffering to reduce the load seen by the on-chip circuitry driving the pad. So latch up is a particular problem near output pads, especially when the pads experience voltage transients above VDD and below the ground. So to avoid latch up, the NMOS and PMOS transistors should be separated by substantial distances and surrounded by guard rings. So here is an example of the double guard rings around folded NMOS output transistor. Input pads also contain an inverter to buffer or to convert the signal from the noisy external world into a valid logic level for the core circuitry. The buffer may perform level conversion. The Schmitt trigger has hysteresis that raises the switching point when the input is low and lowers the switching point when the input is high. Therefore, this helps filter out glitches that might occur if the input rises slowly or it's rather noisy. Another is the bidirectional pads. A bidirectional pad with an output driver that can be tri-stated and an input receiver. The output driver consists of independently controlled NMOS and PMOS transistors. When enable is 1, one of the two transistors turns on. But when the enable is 0, both transistors are off, so the pad is tri-stated. The design is preferably to the 4-transistor totem pole. Tri-state when driving large capacitances. This is an example of a diagram of the bidirectional pad circuitry. And here is an improved tri-state buffer. Another is the analog pads. Analog inputs and outputs connect to simple metal pads and then directly to the on-chip analog circuitry without any digital buffer or driver. Analog pads still require electrostatic discharge protection circuitry. So let's discuss the electrostatic discharge protection. Input pads have transistor gates connected directly to the external world. So these gates are subject to damage from electrostatic discharge that can puncture and break down the oxide. The breakdown voltage was 40 to 100 volts for older processes with thick oxides, but now is 5 volts or less for modern thin oxides. So with a high electrostatic discharge, voltage on transistor drains can also cause punch through, in which the source and drain depletion regions meet, allowing large amounts of current to flow through an off transistor until overheating and permanently damage occur. So the essence of electrostatic discharge protection is to provide a controlled path to discharge high voltages without damaging the gate oxides. So the path consists of extra circuit elements that clamp the input-output pins to safe levels. So, to the non-breakdown devices, like diodes, MOSFET, and bipolar transistors operating in conventional ways, and breakdown devices such as silicon-controlled rectifiers, the SCRs, thick-field oxide transistors, spark gaps, and other devices that break down before the input and output transistors. This is a circuit of input protection circuitry. There is a primary diode clamps and secondary diode clamps. Current limiting resistors, thin gate oxides of the MOSFET. The capacitor is charged to a high voltage, then switch is closed to connect the capacitor to the pin through a resistor. So meron tayong ditong human body model and charge device model. So, sa figure na to, makikita mo yung example ng input and output pads ng circuits. Ayan. The input protection circuitry consists of some resistance, thick oxide transistor, and the drain diffusion diodes of the wide output transistors. So resistances from resistors and some thick oxide transistors. Another is the mixed voltage input and output. The input and output pads thus can include level converter circuits to translate between different voltage standards. If the VDS of a transistor becomes too large, punch-through occurs, possibly causing excessive current flowing until the interconnect melts. So, para maiwasan, transistors with smaller dimensions have a lower punch-through voltage. So, ito yung standards ng single-ended na input and output pads. So, sunod is the high-speed links. High-speed input and output channels. At low transmission speeds, this conductor acts as an ideal wire, or at worst resistance in series that keeps the voltage potentials on both of its ends equal. So, pero sa high frequencies, the conductor can no longer be treated as an ideal wire. Instead, it acts as a transmission line along which the voltage and the current propagate as a wave. A conductor should be treated as a transmission line rather than equipotential net when the propagation delay along the conductor becomes comparable to the signal rise and falls. According to the transmission line theory, the reflection coefficient can be expressed in terms of the load impedance and the characteristic impedance. Impedance mismatch, the energy that has been traveling down the line cannot be fully absorbed or dissipated by the final load. And reflection coefficient is the ratio of the incident to the reflected wave. The phenomenon of one signal energy spilling over into another's energy is referred to as intersymbol interference, or ISI. So in order to suppress such reflections, high-speed input-outputs use channels that are properly terminated at either end of the channel. So ito na yung mga channel noise and interference. Meron siyang types. Una dito is yung dispersion. The channel may attenuate certain parts of the signal energy due to resistance along the conductor and dielectric loss through the imperfect insulator. So, ang dispersion na to, nagli-lead siya sa tinatawag nating ISI o yung intersymbol interference. Another one is the crosstalk. When we say crosstalk, capacitive or inductive coupling causes interference called crosstalk between nearby input and output channels in which energy from one channel propagates into another. So, crosstalk is more challenging than dispersion because the effects cannot be undone unless the coupling mechanism and the aggressor's beat patterns are known to the victims. Next is yung return path effects. When any voltage drop across the return path due to its finite impedance will appear as additional noise to the transmitted signal. Example ng return path effect is yung ground bounce. Bumabalik yung signal. So, after natin malaman yung noise and mga interference, next is yung transmitters and receivers. So, ito meron tayong single-ended transmitters. So, meron siyang type. So, itong first na transmitter uses an open drain transistor operated in saturation with a high output impedance. So, ito namang pangalawa is uses wide transistors operated in their linear regime with low output impedance. And the last one is the line. The line is parallel terminated at both ends. This eliminates reflections at both ends but cuts the output swing by a factor of 2. Differential signaling. So, it is a widely adopted way of improving the noise immunity by representing the signal with a difference between two voltages or currents. Transmitter variations. AC coupling or DC blocking is a convenient way to connect a transmitter and a receiver that have different signal ranges. So, ito yung AC coupling. An example is a receiver that operates with multiple signaling standards. A series of capacitors inserted in the channel blocks the DC content and propagates only the high frequency content of the signal. So, ito yung mga capacitor na ini-insert para magkaroon siya ng high frequency lang yung kinukuha niya. higher data rates. Most high-speed input and output circuits rely on precise clock signals to generate the data pulses at constant intervals. So, dito naman kailangan natin talaga yung clock. So, ito yung mga example ng time interval transmitter and multi-level transmitter. After ng transmitter are receivers. The receiver is typically a simple flip-flop that samples the data at the correct time. For differential signaling, differential flip-flops such as SA, F over F is required to detect small swing signal. Bit error rate. Since the main performance metric for any input and output link is bit error rate, it is the probability of transferring an erroneous bit. This is a eye diagram illustrating bit interval and best sampling point. Clock recovery in source synchronous systems. In source synchronous system, meron kasi yan tatlo. May mesosynchronous tsaka pesosynchronous. In source synchronous system, the transmitter sends a clock signal properly aligned with the data. So, yung signal, naka-align siya sa clock. Example nito is yung the data may be transmitted at the same rate or twice the rate of the clock. So after nung next is yung mesosynchronous systems. There may be difference in delay between the circuits that drive the clock and data signals. As speed increases and the bit interval becomes shorter, the difference in delay occupies a larger portion of the bit interval. Another is place-synchronous systems. In comparison to the source synchronous and mesosynchronous systems, the clock reference for the receiver not only have uncertain phase but also a small error in frequency. So, yung type na yun is place-synchronous systems. So, yun lang.
So, my next topic is about the random circuits. So, this is just an application of a random number generator. So, this circuit is mostly used sa mga lotteries, yun yung ginagamit nila. Itong technology na to is further enhanced para hindi ma-predict kung ano yung lalabas sa numbers. Next. So, this is the circuit of a thermal noise based through random number generators. So, this is run through, yung input niya is thermal noise. So, this is the example of that circuit. Example of TRNG is that it includes measuring atmospheric noise, thermal noise, and other external electromagnetic and quantum phenomena. So, chip identification, basically, it just identifies a chip. So, examples or applications are serial numbers encoded in devices during manufacturing. So, chip ID must generate a binary ID code. So, it must be binary and it must be repeatable and reliable over supply. So, dapat hindi rin siya napipredict. Code length stability must allow a high probability of correct identification of each die. So, the percentage of error must be low. And circuit must exhibit low power consumption and require no calibration. So, applications of chip ID, it is used to detect for branding or counterfeiting or kung may yung mga fake na kung ano-ano. And it is also used in wireless sensor node or network interface card. So, this is the example of network interface card. And this is the wireless sensor. So, advantage is, yun nga, kaya niyang ma-detect yung fake sa original. Tapos, disadvantage is that it can be used, hindi na, pwede niya nang masagasaan yung privacy mo. Ayun.